I will talk about physical prevention of sea lice. We just made a chapter in the new sea lice book called this. My co-authors is Lars Helge, Samantha, Tina, and Luke. But of course, a lot of other people have been involved in the work we've done. Where are the lice copepodids? Where are the salmon? How can we mismatch them physically? By using skirts, snorkels, submergence, lure them by light and feed depth, semi-closed cages, and combine some of these, do it dynamically, and according to the site environment. That's what I'm talking about. This is where the lice are, the copepodids. Can you see them? Far up in the fjord, they're under the brackish water, in the halocline. Further out, they are closer to the surface. So if we put the fish close to the surface, we get like 14 lice per fish after 12 weeks. If we put them like from 4 to 8 meters, then we reduce it to 1/3. And so on. The deeper we go, the more we reduce the infestation. So why are the lice copepodids high up? Because they swim up. Because they want to be where the light is. But we see that they swim up in darkness as well. So it doesn't have to be light for them to go up. If we increase the pressure, like Andrew did, then they're swimming faster up. So they don't like to sink very deep. If you change the temperature, it doesn't matter for the copepodids. It matters for the Noplia. They like colder temperatures, but not for the copepodids. And they the copepodids gradually avoid lower salinity. That's why they are just under the halocline when the brackish water becomes brackisher. Where are the salmon? They like to be warm. But if we go to Tasmania, it's too warm, so then they try to avoid it. So they'd like to be at 16 degrees, if they can. So here's an example. You see the temperature graph here. You see it's coldest at the surface and warmer deeper down. And these fish are deeper down, deeper down, deeper down at daytime. But at nighttime, they go more towards the surface. At the bottom there, you see that they're all at the surface. Why is that? It's the question, answer. Because of the temperature, it's highest up there. Good. I'm trying to wake you up a bit as well. Okay, so creating mismatches between the lice copepodids up there and the salmon, you can do different ways. You can use skirts, and if you're using skirts, they are down here, you see that the lice levels are reduced. Here the effect size is showed as the log response ratio. So all these are studies that are published. So of course there's lots of data around, but these are the published ones. So they show that deep lights and feeding, illustrated down here, schematically, can reduce it, but not as much as the skirts. Submergence reduces it more. Snorkel cages, even more. I'll show you all of these afterwards. Closed containment can actually reduce it by 100% reduction. So then those points doesn't fit into this graph, but here are the ones where they have some lice. Did I go through everyone? Submerged? Yeah, I'll come through the details. This is skirts. So at first, we started using skirts for chemical treatments. This is a green dye added, so we see how the chemical is distributed. And then they started using it to keep the lice larvae outside. Here is a modern example. For those who can see well, you can see that there's a white collar here, all around this cage. It's a 200-meter cage, and this white collar, it goes down to, 10 meters in this case. And in the center here, you see some bubbling. I'll come back to that. Skirts can be semi or impermeable barriers, meaning that they block all the water outside, or they can let through some water but filter out the copper bodies. Of course, after a while, it will be clogged with fouling and so on, so they're becoming more and more blocked over time. There's variable effectiveness. Well, they are typically 3 to 10 meter depth. They are variable effectiveness, yeah, so they can have 0 reduction, 25, 30, 81, 85, and so on in the published studies. And it seems to depend on the environmental site characteristics. I'll come back to that. They're widely used because they are fairly cheap to buy. So more than 300 is sold every year. That's quite a bit. But there is issues like water quality. Since you block the water from exchanging, you will get reduced oxygen levels as your fish are using oxygen, especially when it's warm, because then the fish uses more oxygen. There's management issues. Of course, there's more to put on, and you need to clean them. And if there's a strong current, it will lift it up. There's more forces on the moorings, and so on. They're fairly cheap, I said that. Here's an example from a study by a student from Tromsø that we supervised. So reference in June is blue, so that's the oxygen levels with depth and over 24 hours. In controls, it's slightly reduced, but not much. In skirt cages, slightly more reduced. But in July, when it's warmer, you see that it starts becoming red here in the skirt cages, indicating that the levels are going down towards red traffic light. Yeah, towards poorer values. And here in August, even worse. But what you can do about it is you can add aeration, as you saw in the photo. And here we have played with the aeration. It's on, and then off, on, off, and so on. And you saw that the graph went down when it was off. So obviously, it works when it's on. Snorkel cage is a combination of a skirt and submergence. So there's a net sitting at typically 10, 15, 20 meters depth, forcing the fish down, and thereby away from the sea lice larva. But when they want to go to the surface to refill their swim bladders, they can go up through this snorkel and refill. You've heard about this before. This is how we started with the snorkel cages. I was very afraid here at the beginning of the fish all being up here and using up all the oxygen. So I was out at night checking. And then you see the variable versions of it. So these have been presented on earlier conferences. Also partly this commercial cage trials. So here is a typical snorkel cage. Well, 2016 version, I think. 60 meter circumference in 160 meter circle, 10 to 20 meters depth. We see good but variable effectiveness. Sometimes it's only 0, sometimes up to 100. For a whole production cycle, we saw that it was averaging 73%? 75%, yeah. And the effectiveness seems to depend on the environment and where the fish are. There is more than 120 snorkel cages sold, so it's used quite a bit. Of course, there's much more management to them, handling when you put them out, and you need to clean the nets. There's more net. You need a bigger crane to get in there, and it's more tedious to take out fish to sample for lice and other. We have seen that if there's a lot of pressure differences inside and outside, you get sometimes deformations. That's also on the normal skirts, like you get an hourglass shape. But they're fun solutions. Sometimes we've seen more AGD because the brackish water is not inside the snorkel. But then you can add brackish water, but then you can't have a water exchange. So there's not, yeah, that is an issue that you need to solve. Lena saw that we got less tapeworms. That's very beneficial. So it's working, but even now, there's still future fine-tuning to get it more easily managed. So if you need to treat, there's a hassle to take it off to treat. But some have, when the fish is small, you can even treat in this central area as well. Why not submerge? Can we do that with a simple roof? Yes, it works. You reduce the infestation by 75%, but as you see here in the middle graph, the growth was impaired and the condition compromised. And there's a long story to that, but no, it won't work because the swim bladder empties. Here's a full swim bladder, and then during about 3 weeks, it's empty. So then it must swim faster, or it swims tilted, and so on. So no, go. Can we submerge and take them up once a week? They want to get up. So during that week, they'll swim faster and faster and losing more and more air. But they did fine, so it can be done. But we need to do large-scale trials to really prove it. Another option is to make an air pocket down there. Can we do that? Just illustrate it here and here, so that the salmon can refill in this air pocket. What they do is that they go up, fill their mouth with air, and then as they swim down, they put some of that air into the swim bladder. This is more, okay. Did you get that? There's a small opening back there, very thin. Okay, so we tested out first for some weeks and then for a whole year. And this is what our air pocket looked like. Heavy weights to keep it down. And here's the fish up refilling. There's a few papers on it, a very recent one as well. The recent one is for a whole production cycle. So you see here that the swim bladder refilling is kind of, the controls are the gray, yes, and the black ones are the submerged. So they are kind of equal. So they are refilling. Good. And here is the actual refills per day, or averages per week. And here you see a salmon coming up in the air pocket and refilling. Swim speed, if you measure the swim speed, then you see if they're not filling, because they have to swim faster. So swim speed is the same between the controls and the submerged. Typical swim speed, around 1 fish length per second. Did it work for lice? Yes. So here we got a 97% reduction at the peak infestation here in winter. Didn't work that well later on, but the environment here is a fjord, so there's also a helicline that pushes the lavas down. Submergence in a fjord is not always a good thing. It went kind of well enough with the fish. They refilled, they swam at the normal speed, and so on. But as you see here, the temperature varies with depth. So the top graph here shows the temperature. And these lines are indicating the average swim depth of the fish. So the submerged ones are forced to swim from 15 to 30 meters. And they experience a lower temperature here and here. So they grew poorer. So it took longer time for them to reach harvest weight. Even worse, in this fjord, if you look down here at the bottom graph, which is the oxygen, you see that the oxygen down here is down to 55% outside the cages. So it's even lower inside the cages. So that's poor oxygen conditions, and we know that at that level, they will have reduced feed intake. Also, we had Tenacibaculum quite a bit, and that recovered, the surface fish, they recovered, but not the submerged ones. We even got some mortality. And we also know that the immune system can be poorer when you give them hypoxic conditions. So it's not necessarily always good for production efficiency to sink them down, especially not in the fjords. But of course, some places you will utilize the better water temperature during winter when you submerge them. We made some commercial versions, or I say we, it's Aqua Group, but we have kind of been part of it. So there's one called Atlantis. There's made 4 of them. We've done trials. It's working. They made about 20 of this, called Nautilus. They made 2 of this, but the fish is not put in yet. Arctic offshore farming. This is the commercial version, the Atlantis. So here you see half the cage, because the other half is still submerged. It's coming up. In the center here was the pocket. This is a later version. There's the pocket. And you see this cage has been done for 4 or 6 months, and it's just brought to the surface. So generally, it works very well. You can get reduction up to 100% reduction, but often there is some lice coming on. And in this case, we had every second cage was an Atlantis cage, and when they had to treat the control cages, we got a lot of lice on the submerged ones. Of course, large lice. So they were jumping off during handling and jumping on down there. So this was done at 30-meter depth. So this has been at 30-meter depth plus during the half of the production cycle. And they're now doing like whole farms instead. And so far, with the Nautilus cages, they have not treated, while all other farms around have treated 1, 2, 3, 4, 5, 6, 7 times. And those data, I won't show them, but I'll show them next time. We're following it up. Yes. And last one is deep feeding, deep lights, and maybe light skirts as well. So here's some results from a trial made by Samantha. You see that there were no consistent differences when you had deep feeding versus surface feeding. But in a later trial at a different site, you saw that during this period, you saw that the surface cages got most lice, the one with deep feeding got less, and the one with deep feeding and skirt got even less. Here's some very recent results that's not published yet. Tina Oldham, who has done trials where we try combinations, so deep light and deep feeding and skirts, and also dynamic. So when you only use behavioral attraction, you see that the mean reduction is 26%, but sometimes it's plus 72%. So that's typically when you force the fish to be in the halocline. But also at other periods, you have a reduction of 93. Here is skirt plus. That's when we have used several, so used them together. So meaning deep light and deep feeding and skirts. Or in periods, we have removed the skirts and used shallow feeding and shallow light. So that's when there is a lot of brackish water. So kind of trying to work with the environment instead of against it. And also with the behavior of the fish and not against it. The last one is a lot of snorkel cages that we're following now. So here's more data to come. But you see it's clearly reduced. So in the future, we need to combine the lice where we know where the lice copodes are, the salmon depth, plus the physical prevention to make the best at each site. Then we get the best success. And we're also making an app where you can forecast your site environment. But I don't have time for everything. This is the semi-closed floating. That is also working, but it's more expensive. And you need to pump and so on. I want to know more details there. Future. What happens in the future? You could go to the Faroes and get more waves, or you can go more offshore and get more waves. What happens with the copodids? Will they go down, as shown here, for fish larvae and cod eggs and so on? So when there is a high waves, the distribution is much deeper down due to turbulence, or just due to that the upswimming stops. We don't know yet. Can the colpotus, the salmon lice, evolve to, to deeper swimming? Maybe. There is family variation, as shown by Andrew. In conclusion, thank you.